You may recall that our two concerns about our dataset were, number one, where is the center of the data? And our second concern was how close together or spread out the scores were. The concept of close together or spread out is called variability. We now need a way to discuss the average amount of variability in a distribution. Beginning with the concept that our mean is a model, we can begin making predictions. So I am going to choose a player at random from our team with an average height of 5'10" and ask you to predict that player's height. I pick a player at random, you guess his height. I pick another player at random, you guess his height. It won't take too long for this game to get old. Because the mean is the best predictor for any individual in the sample, you should always guess 5'10". Of course, you are not going to be accurate every time, but over the long run, you will be right, or close to right, more often than you will be wrong. When you use a mean to predict or estimate, your prediction or estimate is likely to be off a little. This is because each measurement of the subjects, x in the sample, varies from the mean, m. This is what is meant by the scores have variability. We could also call it error. In fact, we could call it measurement error. Measurement error is the discrepancy between the actual value we measure, x, and the number we will use to represent that value, m. You use the mean to predict that a player will be 5'10", but in reality, he's 6'0". You now have 2 inches of measurement error. Still, despite the error, the mean, m, is always your best guess. So we use the mean as a model. But this tells us 2 things. 1, each x value will have a deviation from the mean, even if that deviation is 0. So we can use deviation scores as a measure of variability. And 2, the more that the scores deviate from the mean, the less well the mean represents reality. A deviation score is the difference between an actual data point, x, and the mean, m. Deviations are calculated by subtracting the mean from each score, x minus the mean. The 6'0" player has a deviation score of +2. A 5'8" player has a deviation score of -2. A 5'10" player has a deviation score of 0. Always subtract the mean from the raw score when you are computing deviation scores. Deviation scores convey 2 things. 1, whether the score is above or below the mean. And 2, how far the score is from the mean. The positive or negative value tells you whether the score is above or below the mean. Positive deviation scores are always above the mean. Negative deviation scores are always below the mean. The absolute value of the deviation score tells us how far it is from the mean. So the deviation score of +2 is 2 inches above the mean. If the mean is 5'10", the person with a deviation score of +2 is 6 feet tall. Here is a normal curve with a mean of 6. Beneath the normal curve, I have created deviation scores above and below the mean. A person with a deviation score of -3 is 3 points below the mean and has a raw score of 3. A person with a deviation score of +1 is 1 point above the mean, and so has a raw score of 7. The deviation of -1 is a raw score of 5. In fact, I could add all of these raw scores based upon the deviation scores on a number line. A large deviation score indicates a raw score that is far from the mean. the deviation of -3 is farther from the mean than a +1. Raw scores far from the mean have lower frequency than scores close to the mean. Frequency is shown by how close the normal curve is to the x-axis. The closer the curve is to the x-axis, the lower the frequency for that score. A score at the mean has a deviation score of 0 and the highest frequency. The raw score of 6 has a deviation of 0. A score far above the mean is a higher raw score. The deviation of +3 is a raw score value of 9. A score far below the mean is a lower raw score. The deviation of -3 is a raw score of 3. Now we can observe something about the mean and variability. Obviously, the closer all of the scores in the sample are to the sample mean, the better the sample mean will predict any particular score in the sample, because the sample variability is less. When the scores are packed close to the mean, i.e. leptokurtic, the mean is a great predictor. When the scores are spread out from the mean, platykurtic, the mean is a less robust predictor. Therefore, deviation scores are a measure of the variability in the distribution. Lower variability equals better prediction.